Hello, my name is Sophie Mentzel. I'm a PhD candidate at the Norwegian Institute for Water Research in Oslo, and this study has been carried out together with my colleagues and supervisors Merete Grung, Knut Erik Tollefsen, Marianne Steenroth, Karina Petersen, and Janneke Moe, and is part of the EcoRisk 2050 project. And we are focusing on a probabilistic risk assessment of pesticides for a Norwegian case study using a Bayesian network approach. We were able to develop a Bayesian network that uses fully probabilistic risk assessment that can predict the probability of several risk levels and facilitate the communication of the risk estimates and their uncertainties, and it can also be carried out for different seasons. So why are we doing this? Well, conventional environmental risk assessment is based often on the calculation of a risk quotient that represents the ratio of exposure to effect. This approach involves the use of single values of predicted environmental concentration, the PEC, and the predicted no-effect concentration, the PNEC, to quantify the risk substance poses to the environment. Uncertainties accounted for by uncertainty or assessment factors. And it is assumed that there is a risk to the environment if the risk quotient is above 1. A more informative approach is provided through probabilistic risk assessment, where probability distributions for exposure and effect are expressed and enable accounting for variability and uncertainty. This is based on Verdonk et al. 2003, and we try to explore this more by developing a Bayesian network model that can carry out a probabilistic risk assessment. A quick reminder, what is a Bayesian network? They are probabilistic graphical models that can show interactions between variables in a network. And as the figure shows, the network includes a set of random variables and their relations through a direct acyclic graph. The probabilities of a node to be in a certain state depends on its immediate parents and is expressed in a joint probability distribution. All of the states are specified in a conceptual probability table that describes the relationship between a child, in this example this is the risk, and the parent nodes, which are exposure and effect in this example. Each possible combination is an entry in the conditional probability table, and Bayesian networks are based on probability theory implementing Bayes' theorems for updating probability distributions based on new evidence. During previous decades, Bayesian networks were recognized as a tool to deal with environmental problems under uncertainties, and they are also able to assist in risk prioritization. A great example for ecological risk assessment of mercury to the Florida panther was carried out with a Bayesian network and was published earlier this year by Carragher and Barron. The main steps of our approach were to fit a log normal distribution to the effect data and exposure data by season, and then discretize the node intervals accordingly and incorporate the distribution in the node. The exposure effect ratio distribution was then calculated by the first equation, and an uncertainty factor can be chosen thereafter that then derives the risk quotient with the equation 2. This way, a Bayesian network model provides a tool for calculating the risk quotients as a probability distribution to account for example, temporal and geographical variability or uncertainty. The case study region is located in the southeast of Norway and is part of the Norwegian monitoring study program NIVA. The Bayesian network was run for the pesticide azoxystrobin, which was the most measured chemical in the Heia catchment. These are the fitted distributions for exposure and effect. Exposure data was provided for the year of 2011 until 2016, and about 53% of the exposure concentration measured were below the limit of quantification in the Heia Becken catchment. As limit of quantifications are potentially indicating that the chemical have been detected, but they're just not quantified. The effect data in this research was derived by a NIVA risk assessment database, and we collected NOx for azoxystrobin for different taxonomic species group and for all species that are related to surface water, and for adverse effects such as growth, reproduction, mortality, and development. We derived these means and standard deviations for the different exposure season distributions and the effect distribution, and we determined the parent node to have 12 states with a range of -10 to 1 for exposure and 2 to 3.8 for effect. Note that these are log concentrations. Exposure and effect distributions were then incorporated in the node in the Bayesian. This is the parameterized and compiled Bayesian network model for spring season with an uncertainty factor of 1. The risk quotient has the following output and is generally below 1, so it can be assumed that there is no risk. The interval of 0.001 and 0.001 is at 11.6%. And if we select the summer instead in the season node with the same uncertainty factor, we can assume that the risk is higher than in spring, but still below 1. Here the probability for the risk quotient to be between 0.001 and 0.001 is 48.3%, and in the following, the risk quotient node output is displayed in a stock bar to facilitate easier comparison. With this, we only want to demonstrate the various alternatives. I'm not a risk assessor, so it is not up to me to select an appropriate uncertainty factor. Anyhow, we selected various seasons and uncertainty factors to demonstrate how the alternatives affect the risk quotient. On the x-axis, you can see the season and uncertainty factor that were chosen, and on the y-axis, the probabilities of the different intervals are displayed. The intervals are also displayed in different colors, ranging from blue, which is no risk, to red, which is risk. The risk quotient, when applying an uncertainty factor of 1, are all below 1, which means there is no risk. But when we apply an uncertainty factor for summer and autumn that are higher, the risk is getting higher, and there is a risk for a scenario where an uncertainty factor of 100 was applied for both summer and autumn. The current Bayesian network model can be improved in several ways by obtaining more effect data that represents more species and especially native species, and using predicted exposure concentration instead of measured exposure concentration. Nevertheless, this approach offers a transparent way of evaluating the required characterization of uncertainty, and it is a simpler way than working with continuous distributions. These examples demonstrate that Bayesian networks modeling is a promising tool for calculation of risk quotients as a fully probabilistic distribution instead of a single value. Also, this approach provides the probability of the risk quotient exceeding not only 1 but also other specified threshold values. The Bayesian network approach can still apply a safety factor. Our planned future or further development of the Bayesian network includes an extension to include pesticide mixtures and assessment of cumulative risk, but also to incorporate climate and agricultural scenarios to predict future environmental risk of pesticides under future conditions. This research was funded by European Horizon 2020, and for more information you can visit the following NIVA website. I would also like to point out some interesting talks from Taylor Lane focusing on impact climate change on chemical environmental fate processes, and Samuel Welch dealing with pharmaceutical environmental risk assessment. Both are PhD candidates in the Icarus 2050 project. and then another interesting talk by a NIVA colleague of mine, Simon Schmidt, about conceptual adverse outcome pathways. And I thank you all for listening.